Yeah. Hello everyone, welcome to a new lecture, our computer learning course. Before we start, let me introduce the graduate assistant for the course. Enough, please. Get the picture.
Hello everyone, my name is Hemant. So I'll be your GA for this course, and I'll be available in the library block first floor. But if you have any questions or any uh, doubts regarding the subject, especially regarding assignments, but not for solving the assignments, to help you understand the assignments. Okay. And I have two more small things to let you guys know. First thing is, I would humbly request while you submit the assignment, do it on your own. Okay. The main intention of the assignment is for you guys to understand the subject and try to put it down in that assignment. If you just copy, then you'll get penalty, and I'm not responsible for that. And the second thing is, while you submit, please, if you go to the assignment bottom, there will be instructions given very clearly saying you have to submit a PDF, which is a report which you have to make, and the code, the actual code file, and the screenshots or whatever is needed. So please follow the instructions. That's all. And I'll be shortly posting the PA hours for the subject in the announcement section in the Canvas. Alright. Okay. Any questions?
Thank you very much.
Can you submit this? I mean, in the Word file? Yes, but PDF is more preferable. Yeah.
What is it?
They want submit in Word document rather than PDF.
Well, the PDF is more universal, so it will not be get affected by any problem. But the Word can open on Windows, can have some problem with the Mac, because it's not universal. The PDF is universal. Once it's generated, you can open it on any platform. Okay, that's why the PDF is better.
Last time I got found a lot of corrupted Word documents. They have submitted it, but I can't open it, so I can't create it. That's the problem. Okay. Thank you.
Actually, you need to learn even for your resume or your CV your CV. Don't submit it as a Word. Always work with the PDF. Okay, PDF considered to be universal and it will not suffer from any problem or any platform. Okay.
So do you want me to take it in and solve?
No, I'll take it. No worry. You
Can
can.
I?
Okay. So last time we learned about the image, how the image can be stored on the computer. And we stated that there are two types of the images. There is grayscale image, there is color image, and each one of them can take different way to be saved to the computer. We said that the grayscale image is a 2D matrix or array that has number of rows, dimension, number of rows, and the number of columns. And each pixel in the image can be considered as 1 byte. So 8 bits, 1 byte. So the value for the pixel can go from 0 to 255, which are the minimum. 0 is the minimum value for the pixel, which is the black color, and maximum 255, which is the white color. In between, any number can include a gray level, shades of the gray, depend on the illumination. Okay. Regarding the color image, on the other hand, it consists of 3 layers, 3 basic colors, which are red, green, and blue, R, G, and B. They are working together to build the whole entire image. So each one of them is 2D. So this is 2D, this is 2D, this is 2D. Each one of them is 2D. So when we combine them, it ends up that we have 3D vector, 3D array, m by n by 3. Okay? Is this the only way we can represent the color image? The answer is no. There are many other ways or other domains. Again, the basic concept or the basic problem or the basic idea that you are using to represent the color image basically come from the arts. So the arts are the people told us what are the basic color we can use. And if you study any kind of the art, you will learn that you can combine different bases, okay? But for computers, those three basic color considered to be the main three. We can make another combination from that. Like there are other representations for the color image, not using those three basic color, but again, we will not cover them now. When we need them later, when we go to the deep learning, we will discuss them. But even this one used also for the deep learning. The problem that we discussed last time was the quality of the image. When we look to the image, we see some place or some pixels are dark and the others are white. Some of them have object that we can't recognize, and the other have good lighting, we can recognize the object clearly. And we said to can solve this problem, we have another view to the image, which is a 2D function. So we can consider the image also as a function of both X and Y. So we can consider that we have two coordination, the X coordinate, the Y coordinate, and the pixel values here considered to be function of both X and Y. Based on that, we can change or transform this function to another function. We will call it G X or Y. This is transform, which is G of X or Y that can change those pixel value to different value that we can recognize and work on our application. And to do this, we introduced last time two techniques. The first technique was the alpha beta technique, where we said we can have a new image or new function, G of X or Y, which equal alpha times f of X or Y plus beta. In this case, based on your choice of those two parameters, alpha and beta, I can decide the new generated image. Like here, if I assume that alpha equal 1 and beta equal 20, this one will be converted to this one, okay? What is the problem of this technique? This technique has two problems. Problem number one, there is no guarantee that the maximum value for G of X or Y to be 255. It has to be 255 because we have what? We have a maximum value here. We can't go over it, okay? If the value go over 255, what will happen? If you have 1 byte to represent your data and you added more to this value, what will happen? This is a very common problem in computers. What?
Out of one.
What?
Out of one.
Data overflow. Okay, so the value here can return back to 0 and the overflow flag will trigger, which means that you will lose your data completely. Okay, so we have to do something to prevent the maximum value to stop at 255. What we can do, if we are using the alpha beta technique, is just add an if statement here. If the value of G become over 255, crop it at 255. This is a good strategy? The answer is no, because in this case, we will have many pixels converted to complete white. Okay, this is the first problem. What is the second problem? The second problem is that here, most of the pixels or all the pixels are changing equally. So this is dark and this is light. In this case, I'm processing both. the dark and the light. But I want to process this more. So I want this to be lighter. This lighting part is okay with me. I just want to work on this part only. Okay? So this technique has two problems. First, it's working on the whole entire image. It doesn't work on regions. Second, it can overflow. It can go over the required limit of the pixel. That's why we came up to the second technique, which is the gamma technique. What is the gamma technique? We said that we can do the same game, but in a different way. How? They said, let's do normalization first. So I will divide the value of the pixel over 255. Why 255? Again, because it's the maximum value. Okay? So this value will always be a fraction. Always. Okay? The maximum value it can achieve is 1. If the value of the pixel is already 255, this will be 1. But if it's lower than this, it will be fraction. The minimum value it can be achieved is 0. Okay? Now, this become a fraction. Now, what will happen if I make this fraction to the power 2? So when you have fraction, we put it to the power 2. This fraction will what? Reduce in value. If it's half, it will be 1/4. If it's 1/4, it will be 1/16. If it's 1/16, it will be 1/64. So it's reduced in value. So if this gamma is bigger than 1, this fraction will reduce. Now, if I multiply it back times 255, again, I will produce another value for this pixel, but this value is lower. So if if our gamma here is bigger than 1, we are darkening the image. Right? Because the fraction, when I put it over power greater than 1, this fraction will be smaller. Smaller times the same number here, it will give you lower value. So the image will be darker. What if I put it to a value lower than what all this means? If I have it to 1/n power half. Let's take an example. 1/4. If you have 1/4 power half, this will give you half. The value will increase. Okay? So if the value of gamma is less than 1, this will make lighter. So if you want to lighten your image, put the value of gamma less than 1. If you want to darken your image a little bit, put the value of gamma is greater than 1. What if gamma is 0?
Always return with 255.
What that?
The value will be 255 always.
Exactly. I'm converting all pixels to 255. So the image will be complete white. So gamma cannot be 0. Okay? So it has to be bigger than 0. Can it be lower than 0? Can it be negative? If you put it negative, you are flipping this fraction, right? This means you are destroying the fraction or the normalization constant. So gamma can't be negative. So it has to be greater than 0 and a positive number. If it's a fraction from 0 to 1, in this case, I'm lightening the image. If it's greater than 1, you are darkening the image. Can it be 1?
image will stay the same.
We are doing nothing. So if gamma equal 1, there is no enhancement. Okay? Is this clear? Any question about this? Okay. Now, compared to the alpha beta technique, we said the alpha beta technique suffered from two problems, right? What was the first problem? What is the second problem? First problem was overflow. Second problem?
Works on the whole image.
Exactly. It's not regional, it's work on the whole entire image. Now, the gamma technique, did it solve the first problem? Do I have overflow in this technique? No. So, check, overflow problem has been solved. How about the regional? Will it work on some area and ignore the others? No. So, still suffer from the regional problem. Okay? So, the gamma technique, it's better than the alpha beta because it prevents the overflow. But it's still working on the whole entire image. So if you are lightening the whole entire image. If you are darkening the whole entire image, which is still a problem. Now the question is, can I modify the technique to work on some areas? With some areas, yes, and with some other area, no? He said, yes, we can. In this case, we will divide the image into regions. And we can have different value of gamma for each region. So this area will be too dark, so I will lighten it a little bit. This area is okay, I will keep it as it is. This area is a little dark, I will lighten it a little bit. This one is okay, I will leave it. So I will put gamma equal 1 here, gamma equal 1 here, gamma equal half here, gamma equal half here. Okay? So we can divide the image into sub-regions, and each region will have a different value of the gamma to work over it. So yes, we can overcome this problem. Some people said this technique is okay, good, but it has one problem. What is this problem? If you look to the value of the pixels, the value of the pixels starts from 0 and ending at 255. Now, each color in this grayscale represented somehow in this pixel. But are all of them represented in the pixel? Or some of them represented and the others are missing? They said, we don't know. How can we know if all those gray levels included the image or no? They said, we need to measure something called histogram. So the histogram is a statistical technique to measure the frequency of occurrence of a specific event. Here, this event is our pixel value. So we will have all pixel levels starting from 0, ending with 255. And for each value, I will measure the frequency of occurrence of this color level. Okay? Why this is important? Because if the image is dark like this, in this case, I will see the histogram for it to look like this. So this means that most of the colors concentrated in the dark area. So if you want to lighten them a little bit or make it lighter a little bit, I need to push this curve down to expand it this way. Again, I can't change the energy under the curve. This area, I can't change it. Okay? But I can work around it. How? By pushing it down a little bit, so it will be expanded. So if this curve expanded, like this. In this case, the number of pixels, the number of dark pixels will almost equal the number of light pixels. So the image will be balanced. Okay? So that's what I want to do, to make this balance between the dark and the light. Can we do this mathematically? He said yes. How? They said simply, I will treat this histogram exactly as I'm treating it in statistics. So how we treat the histogram in statistics? They said the histogram by default, if you normalize it, meaning if the number of pixels here, for example, 64, yes, 64. In this case, I will divide all the value of the frequency over 64. So if we assume that this level, let me turn it back to the right. If assume this level is, which is level 1, it was 10 pixels. Then level 10, it was 5 pixels, and so on. In this case, if you add those numbers together, the total number must equal 64. So I'm dividing each one of them of 64. So it will be 10 over 64, 5 over 64, and so on. In this case, if we added this value together, the sum will be what? 1. Now, this will look similar to a function we have in statistics and probability called the probability density function. Okay? What is the properties of the probability density function? It has to satisfy 3 conditions. First condition, it must be greater than 0. So any value here must be greater than 0, which is already satisfied. Do we have any 0 values here? No, all of them fractions, but positive. Second, the value, all of those values must be less than 1. Is there any value here will equal 1? No, because we are dividing all of them over 64. So they are fractions. The sum of all of them must equal 1, which is again correct. We are measuring the frequency. So the total sum of all of them will equal 1. Then we have a typical probability density function. Okay? Now, can I modify this probability density function to look more flat, like uniform distribution? If we do this, voila, we did the perfect histogram equalization process. Okay? The honest answer is no, we can't make it perfect, uniform. But we will try our best to flatten this a little bit. How can we do this? They said the first step, you have to calculate the histogram for your image. So we will assume that this is our image, which is a smaller image, which is 8 by 8. Very simple image. I calculate the histogram for this image. How? I will check all the pixel value starting from 0 to 255. If you add, for example, the value of 0, does any pixel here represented by 0? Do you see any 0 here? No. So the frequency of the 0 is 0. 1. Do you see any value of 1? No. 2, 3, 4. If you keep doing this until you arrive, to 52, all the previous value was 0. They didn't represent it here by any chance. When you start at 52, you will see that it has been represented once, which is this one. Then 53, 54, zeros also. 55 represented 3 times. 1, 2, and 3. 58 represented 2 times. 59 3 times, 60 1 time, 61 4 times, and so on. Again, this is the maximum value achieved, but we should go even further. 155, 156, and so on. But the frequency for those will be what? All these. Okay? Now, if you plot this on a graph, you will have your histogram. So the histogram is nothing but plotting this table. This is the X value. And this is the Y value. What's going on? If you plot this on the X-axis and this is the Y-axis, you will get this shape, something like this. Okay? If I want to show it to you, that's how it will look like. Okay? Again, it starts like this, and for the high representation, here we are stopping at 150 something or 160. But if we keep going, it will see zero values. Okay? Now, how can we convert this into this flat distribution? This said, simply, I will calculate the CDF, the cumulative distribution function. What is the CDF? From the definition of statistics again, the CDF is the sum of the value at specific pixel plus all the previous. So the CDF of 52 is 1 because all the previous value was 0. The CDF at 55 should be 4. The CDF of 58 should be 6. So this and plus all the previous. Okay? So the CDF should always grow. It should never reduce. Okay? It's always growing. So we will build the CDF function for this table. So for 52, it was 1. For 55, 4. 58, 6, 9, 10, 14, and so on. As you can see, it's always growing. The final value must be the total number of pixels you have in the image. Must. Okay? Because it's the frequency. Will it be another number? If this is not the total number of pixels, then you have something wrong. Okay? Now, I did the CDF, how this will affect the normalization process. They said simply, after you calculate the CDF, you will substitute to this formula. What is this formula? This formula says the newer value of a specific old pixel value, and this is H, is new. So the V is the old. The H value is the new one. This new value of this old value equal the value of the CDF at this pixel value minus the minimum value of the CDF divided over M by N. Why M by N? What is M and what is N? Roll code of Rosen code of what? Of the image, right? This is equal what? 50. This last number. So M by N is nothing but CDF maximum. Okay? So CDF maximum equal M by N. So CDF maximum minus the CDF minimum. Actually, what we are doing right now in this expression is a normalization process. And memorize this formula. When you are normalizing any image or any data, this is one way to normalize it, by subtract the value minus minimum over maximum minus minimum. This is one of the most important normalization technique. The value minus the minimum value over the maximum minus the minimum. Okay, so what we are doing here is just normalizing the CDF. The value minus the minimum over the maximum minus the minimum. This is similar to what? Similar to this. Exactly the normalization that we did here. Okay? So we are doing normalization now. Then we will do similar to what we did in the gamma. What did we do after the gamma? Multiply it times the number of levels. Minus 2 or no, this is a different discussion. Some people say we should subtract it from 2 because we will do rounding. Some people say no, don't do the round and remove the 1 and just multiply times the 255. Okay? So here, the number of levels, which is this L, should be 255. So 255 minus 2 plus 1, which is actually 254. Okay? And using the round to guarantee that it will not go over the 255. Okay? So if we did this, we will change the old value of the pixel to a newer equalized value. If we apply it to one of the examples that we have, so let's talk about the first one. First one is 52. So h of 52 will equal, round of course, 1 minus the minimum. The minimum is what? Over 64 minus 1 times 255. 1 minus 1 equal?
0.
0 over 63, 0. Let's go to the second one. Round of 4 minus 1 over 63 times 255. This is equal 3. 3 over 63 times 255. Can you check it over the calculator? Three times 255 over 63. It's equal 12.1. Rounding equal 12. Okay, so you can't keep repeating this for the rest of the table. I will remove this value, replace it with this new value. Remove this value, replace it with the new value. Okay, then whatever you achieved here, put it back in the image. So that's how the image will look like. Any value that was here, I replace it with a newer value I calculate from the table. Any value was here, replace it with a newer value from the table, and so on. Now, if you calculate the histogram for this new generated image, that's how it will look like. You see this one? All the pixels concentrated in this small region. Here, I'm going until 255, so here. 255, here it's only 160, by the way. This is the maximum value here. Here, we are going until 255. You see, they are distributed over all the spectrum, not shrink it into one area. No, it's spread it over all of them. Okay, so as you can see, the image now including a variety of gray levels from all the spectrum. Now, did we now solve the first problem, which is the overlap overflow problem? Yes, no overflow here, because we guarantee that the maximum value will go 255, no more than that. Did we solve the regional problem?
Yes.
Are we working on region from the image only? We are working on the entire image, right? So the regional problem still exists. So the histogram, yes, it's adaptively try to distribute all the value over all the pixel levels, but it's working on the whole entire image. It's not working on a specific region in the image. That's why it still suffers from the regional problem. Can we solve this? They said yes. We will do exactly what we discussed a couple of minutes ago with the gamma. With the gamma, I told you can do what? Divide. I will divide the image into blocks. Then I will do histogram equalization for every single block separately. So I will work on this block by itself, do histogram equalization. Work on this block, do histogram equalization. Do histogram equalization, and so on. Okay? Then I will combine them back into the image, into the output image. So each one of them will be equalized based on the required distribution. Again, this was good, but they found that when we try to put them back, they are not matching well, and they're still. So if you find the histogram of the whole entire image, you will see that the dark area will still be dark. The light area will still be light. It's not homogeneous together. That's why they came up with this another type of histogram, which is a clip limit adaptive histogram. What is this clip limit adaptive histogram? They said, if I have an image and I want to do histogram equalization tricks, the first step, I will divide it into regions. As we said, to guarantee that I'm not working on the whole entire image together. Then, for each region, I will calculate the histogram for it. Then, I will set a limit for this histogram. And I will crop any pixel value above that limit. Okay? But remember, when I told you about the histogram, I told you that we can't cut parts. We are pushing it to make sure that the power still exists and distributed over the others, right? Now, will this clipping solve the problem? The answer is no. Now I'm removing some part of the area, which is a disaster in this case. How can I solve this? They said, I will feed this area back. So as if I'm shifting this up. So this area will be added here, and I will shift this part up a little bit. So I'm not wasting the area, and throw it in the garbage? No. The area that I'm cutting from the histogram, I will add it underneath. That will make part of the lower pixel value higher a little bit. But it will also push this area up a little bit. Right? Agree? Then I will cut this part again and push it underneath here. And I will keep doing this until I make sure that all of them within the limit of the cropping. This will be my recent histogram, and this is the one that I will equalize. So I will equalize this histogram for this part. Then I will do the same thing for the next part, for the second part, for the third part, to have an equalized sectors, each one of them within this clip limit. So this way, I'm enforcing the frequency of the levels to be within this range. Don't go over this. Now, if you put them together, unfortunately, they will still be a little bit mismatching. That's why we will need a kind of interpolation, which is another technique. We will come to it later, to can make them homogeneous. Okay? But this technique is a very well known nowadays, which called clip limit adaptive histogram equalization. This is one of the state of the art of the recent technique we are using now for the histogram equalization. So instead of working on the whole entire image, no, I'm dividing it and enforcing it to be within some specific clip limit. But at the end of the day, I'm doing the same exact histogram equalization technique that we covered here. Okay? Any questions? Any problems? Okay. Now, the question should be how I can do this encoding, how I can read the image from the code, how I can modify with the code to build the alpha beta technique, how to build the gamma technique, how to build this histogram equalization technique. Now let's see a small sample example for this process. First, we'll start with the image read. Give it a second, it's opening. Did all of you install the Anaconda on their devices and ready for the assignment?
Yes.
The assignment on Canvas right now.
Who's locked?
Sorry?
Who's locked?
Locked?
Assignment is locked.
Okay, I'll double check it. Okay, please check again. finally. Okay, so how I can read the image first. Again, as I said, for now, I don't want you to use the OpenCV for reading the image or doing any modification with it. So we will use the PIL image library to read the image from the hard drive. Okay, so the first step is you will use the image package to open the file from your hard drive. This way, you have now the image as data in your RAM. Unfortunately, until this point, the data in the RAM as an image object, not as a matrix. Okay? You still can get information from this image object by, for example, getting the dimension of the data, change the color color space as an RGB or an grayscale, and play with it, but it's still it's an object. Okay, so the data is still embedded inside it. How can we convert it to a matrix or an array that we can work on with it using our traditional technique by using the NumPy array? Remember the NumPy library that I told you to install last time? So you will use the NumPy library to convert this image object to an array. It will be converted no matter what type of the image. If it's a grayscale image, it will be converted to 2D array. If it's a color image, it will be converted to a 3D array. Once it has been converted to array, you can modify it however you would like. So for example, I will add a breakpoint here. Actually, let me remove this. You run it first, then I will debug it. So I add a small breakpoint here, so I can see the dimension and everything on the other screen. So the image itself, if you look here, it's a JPEG image file. So it's an object, image object, still has its own information. That's not what we want when we work with it in our course here. We have to convert this object into array. How we will do that? By the conversion of the NumPy array. So in this way, it has been converted to NB image, so it will be converted to NumPy array. If you want to see the property of this NumPy array, you can go inside here and check all the information you like. So the dimension of it is 512 by 512. The data type or the information inside is unsigned integer. What is the meaning of unsigned integer 8? This computer data type. You should be aware of this data type. What that?
Positive numbers.
Okay, unsigned integer is positive number, right? But what is the meaning of 8? 8 pixels. Sorry, 8 bits. Okay, not bytes. 8 bits. So this means that each number is a byte, only 1 byte. Okay. Okay. The maximum value of the matrix is 26. The minimum value is 0. Okay. Now I'm having an array, 2D array of dimension 512 by 512. You have the freedom to play with it. Okay. What you want to do, you can add any value to it. Like the maximum value here is 26. Let's add. Let's first iterate over the value. If we iterate over the value, what should happen? 2D array, you will iterate using 2 nested for loops. One for loop for the rows, another one for the columns. Okay, it's a typical 2D array. For each pixel value, I can do any modification I want to do here. This modification can be by adding values. So for example, I can add 20 as an example. I can print the value after modification. I can do anything I would like. So after modification, added another breakpoint, so I can see the maximum and minimum as well. Okay. Again, stopped at the first breakpoint. Now I will run it, so it will go to the next breakpoint. Now it's iterating over the image. It's showing it. And now it's stopped at the next breakpoint. Not yet. Stopped or no? Oh, actually, I pressed complete run, which was not correct. Okay. I cleared this one. Yeah. Now it's done. Okay. Now, if you see the newer NB image, the maximum value is 46. The maximum value for the previous one was 26. Now I added 20 for all the pixels, so the maximum value becomes 46. The minimum value was 0. The minimum value here is what? 20, because I shifted everything by 20. Okay? So here I can adjust this value and this value, which are the alpha and beta parameter in my enhancement. Okay? So this is the first technique of the alpha beta enhancement. Okay. Again, I can print the value after that or show it using the matplotlib. Remember, we told you the matplotlib is our tool to view the image. So using the matplotlib, I can show it, but watch out because the default configuration of the matplotlib, that's you, the default configuration of the matplotlib is not gray. The default configuration is color. So if I just remove this, the CMap gray, it will show you a purple image, something that doesn't make any sense. That's why we need to add this part, which is the CMap gray. Okay? Then using the block.show will pop up the screen for you so you can see the image. So if I want to run it step by step, it's the step. See? Now I have the image show this. Okay? Now, if I want to run the gamma technique, what should I do? What is the modification I need to do here to run the gamma? Where should be my modification? Can you see the screen?
Zoom in a bit.
Yeah.
Zoom in.
It's okay? So, which part I need to change for to convert this technique into the gamma technique?
Line number 23.
What should I do with it? This is the current line value. What should be done with it? Well, so here I need to divide the value over the 255 for normalization, then make it power gamma, then multiply 10 times 255 again. Okay, so this is the line that you need to modify. Okay. Let me return to the original view. Any questions so far? Okay, how about the histogram equalization? How can I do it using this technique? Again, it's exactly similar to the other application. Once I read the image and convert it to array, I can do everything I want. Now it's a programming matter. Okay, so first I will start by reading the image as object, then convert it to an array. Then I will do exactly the steps that we discussed. So I will start by calculating the histogram. So for the histogram, I'm just iterating over all the value in this array. And if I found any value, I'm just increasing the frequency of this value with 1. Very simple. Okay? This is the histogram value. After that, I'm calculating the CDR, which I will start by empty array or empty vector, have the same size of the number of pixel value, sorry, level value, which is at 255. Then for each one of them, I will follow or accumulate the value over each other. Again, this is organized and sorted. So all what I need to do here is what? Just add any value to the previous one. That's it. Very straightforward. The final step is the normalization process. So the equalization process. The equalization process is what? Is applying the equation. So I will just apply the equation that we introduce. That's it. You will have a new image which is histogram equalized. Okay? What if we divide it or ask you to make the clip limits technique? Where exactly I need to do the change? Which part need to be changed to go to the clip limit technique? Remember, with the clip limit, first I'm dividing the image into regions. Step 1. Step 2, I'll calculate the histogram for the region. So this should be done. Step 3, I'll do what? Clipping limit. Okay? So after calculating the histogram, I have to iterate over the value of the histogram and crop them. And any value I will crop, I have to store this value to add it underneath over all the other histogram value. Then I will keep adding it or doing it again and again here. Then I will go to the CDF part. So any modification should be done here in this part after going to the CDF. So after the histogram value and before the CDF within this area. Okay, which is cropping and adding that underneath. Okay. After that, it's too straightforward. Calculate the CDF, then use the formula to the equalization. So the only difference between the clip limit and the regular histogram that we are cutting into regions, step number 1, then we crop the histogram at some specific value and add this area underneath all the spectrum and keep doing this until all within the limit, then follow the other steps. Is this clear? And watch out, because this histogram equalization will save your life in some places. Seriously. So in some job, in some task, especially in the medical field, if you are working for medical company, this histogram equalization technique is a real life saving. It will solve so many problems. Okay? Any questions? Okay.
Sir,
Hmm?
like we are dividing the image, right? In the creeping. So in how many parts do we have to divide?
This is something that you should decide.
Okay.
This is what we call a hyperparameter of your selection. So if the image is too big, you divide it into 8 parts. If it's smaller, 4 parts, depend on your selection. Okay, now let's back to anyone have any question about the image enhancement? So we usually do this image enhancement technique before applying any of the computer vision algorithms that we will cover. So this is an essential step that we do it earlier, before the algorithms, okay? Now, we want to understand what exactly we want to do with the image right now. To do this, we go one step behind. Remember when we said that the image is array, we just keep saying this image is array, right? Now, when the image is captured by the camera is what? Hole that has lens which collect the light, right? Right? Now, when this light projected onto surface, will it be projected as pixels? Now this means when I'm talking about 512 by 512, when I'm having 512 by 512 image that I just show you, this means that those are the total number of rays that I could collected, or those are the total number of rays came through the camera? Like your eye only captured this number? Just no. We have unlimited number of rays coming through the hole. Okay? So the number of rays coming from here to here is unlimited. So there's so many. So why we are capturing only this specific number in this case? Why are we capturing the 12 by 12 or 13 by 13? Why are we capturing this number? And the answer for that is the sensor itself, the digital world. So the architecture of the camera, this modern digital cameras, is we having lens, and the ray is collected with the lens projected onto a sensor. This sensor is nothing but an array. Okay? This array consists of CMOS transistors. Those CMOS transistor is a photovolatile, meaning they will turn on the gate when they receive a light beam. So if a light beam drop on this transistor, it will turn on. Same thing here, same thing here, same thing here. Okay? Now, one beam will hit this one, but thousands of beams will miss those. Right? This is considered to be one of the big problems in the digital camera, that the number of transistors we have in the sensor cover only about 50% of the area of the sensor. Okay, so we are missing almost half the number of rays we are collecting. How this will affect us? Actually, it will cause a bad problem for us. What is this bad problem? Assuming that I'm capturing image right now on the sensor. So one ray will come for my head, then it will miss this part. The next one will come here, miss the next. This here, miss the next, and so on. So for me, I will be cropped. Can we have a definition for that? Mathematically, they said yes, we can call it aliasing. That's how it looks like. So you see this? Can you see this waving? This is the aliasing. And this is a big problem. If you can remove this aliasing, now this is the surface in real world, right? If you look to this fabric with your own eye, it should look like this. But unfortunately, it will look like this for you with the sensor. So this is called aliasing problem. Can we remove this aliasing problem or overcome it? The answer is yes. How can we do that? They said, let's go a little bit in math. This problem of math is a very well known as the sampling problem. So, assuming that I have a signal like this, this is a regular sinusoidal signal. Okay? Now, if I want to convert this signal into digital, this is a digital signal or no? Why? How we define the digital signal? How we can say that the signal we have is digital or analog? Okay. There are two things we need to watch for the signal. First thing, the time. Second thing, the value. If the signal is discrete in time, quantized in value, then it's digital. So the digital signal is discrete in time, quantized in value. If the signal is continuous in time, continuous in value, then it's an analog. Okay? So digital signal is discrete in time, quantized in value. So I should run this. The analog should be continuous in time, continuous in value. Okay? Now, for this signal, which I have in the blue, is it discrete or is it analog or digital? Analog. Because on time, it's continuous. There is no breaks at any time points. And in value also it's continuous. Yes, it has upper limit, but it's continuous. There is no break at any point. Okay? Now, I want to convert this signal to digital. Someone say, okay, I will sample it. What is the meaning of sampling it? Meaning, I will stop at some point and take a sample. So based on that, someone did this. So he stopped at this time and take a sample. They stopped here and took a sample. Here took a sample. Here took a sample. He was not lucky. Why? At this time, the sample was 0. At this time, the sample was 0. At this time, the sample was 0. So if I get rid of this one, can those values represent this signal? The value that I can see right now is what? 0, 0, 0, 0, 0. If this is the original signal, how it looks like, all zeros? No. This means I destroyed my signal. The original signal, which has several values, have been destroyed. I lost it forever. Okay? So what I did here is a bad sample. Someone said, okay, the problem now on the place I'm taking the sample. So I will take the sample like this. Instead of taking it at every point here, I will take it in a shorter time. Okay? Now, the value, the first value is this, the second value is this, the third value is this, the fourth is this, the sixth is this, and so on. Now, does this consider as a good sampling technique to the image? Sorry, to the signal I'm having? Let's plot this. Does this red good representation for the blue? No, we destroy it. Okay, even if it's not zeros, but we destroy it. Because the other one is short in time and has so many values in between. We just got those two values. So we destroy the signal. So how many times I should stop here and take samples? They said we need to build something, a relation. So if I have a signal like this, I have to take number of samples that be a good representation of this period? Is there a relation for that? The answer is yes, which is something called the Nyquist rate, which is the sampling rate. The equations say that the sampling rate must be greater than or equal double the maximum frequency I have in my original signal. So it should be something like this. You see how many samples I'm taking from the image? Lots of samples. Why? Because this signal has a high frequency. Okay. Now, this is regarding the signal. Now, with the image, if I do this, will I have a good result? The answer is yes and no. Yes, it's a good representation, but you will still suffer from this problem. Can I get rid of this problem? The answer is yes. How? By using something called filters. So we need to understand what is the concept of filtering and how we can use it to improve the quality of our images. Okay? And we will do this after 10 minutes break. Okay? Now we will come up to another concept, which is the image filtering. What is the meaning of image filtering? Image filtering means I want to work on the image to remove some information or extract some information from the given image. How can I do that? By combining the pixel value of some position with the neighbors. So this is the concept of filtering. Like for now, I'm having the image like this. For this region as an example, I have this pixel. So I want to combine the information inside this pixel to its neighbor somehow. How many neighbors? Debatable. Some people say the 9 neighbors, some people say the 15 neighbors. So depend on the number of neighbors I want to include. But the concept is combining information of one pixel with its neighbor and replace it in a newer version. So this is the old. So this pixel will be replaced with a newer one, which is this combination. So here I'm having input image and output image. This input image will have some hidden information. I want to extract it. The output image is the clear one that has what I need. So this can be used in many applications. It can be used for edge detection, for corner detection, to removing the noise, to make enhancements. So we can use it in many things. But the question is, how can this be done? So the main point is, I'm having one pixel, and this pixel, I will apply a filter to it. So a filter that will be applied to this pixel, so I can replace it with a newer one. This filter is a function of this pixel and all the neighbors. Okay? Now, in math, How can we call this? This can be called in many ways. One of them is cross correlation. Another one is convolution. Are they similar? No, there's this one small trick between convolution and cross correlation that we will cover in a second. But in both of them, this is a linear filtering. Why linear? Because I'm combining the information of this pixel with the neighbor linearly. What is the meaning of linearly? When I can say the function is linear? When can I say that f of x is linear? What is the condition of function linearity? It has to satisfy two conditions. First thing, f of a of x equal a of x. If I replace the x with a constant times x, in this case, the a will be kicked outside. The second condition, if I have f of x plus y, this is equal f of x plus. What's wrong? Plus f of y. Okay? If only function satisfy those two conditions, we can call this function a linear function. Okay? Now, if I'm just combining those in a way of addition and subtraction with some weights, if these are linear weights or a linear combination, the answer is yes. Okay? So this process, as I said, will be done through a convolution or cross correlation, where we will replace each pixel with a linear combination of its neighbor. As an example, if you have this image, I want to replace this with a newer value according to this filter. So I will multiply each pixel here times the corresponding value here. So it will be 0, 0, 0, 0, 0, 1, 4, and 3. So it will be half times 6, 3. Half times 8, 4. 1 times 1, 1. All the others are 0. Add those, equal 8. So now the newer value here is 8. That will replace the 6, which combine value from here with those 3 values. Okay? This is the concept of filtering the image. This function or this linear combination can have several names. One of the names is kernel. Another name is mask. Another name is filter. Name it however you would like, it doesn't matter. All those are correct names. But what the function it's doing is just linear combination of those pixel values. Okay? Now, if we apply this filter or this mask directly to the image the same way I show you, this is called cross correlation. I get the filter, apply it over the mask, over the image directly. So I apply it here over this and multiply them 0, 0, 0, 0, half, 0, half, 1, 0. Multiply each one times the corresponding one, add them, produce this. The way I'm showing you right now is called cross correlation. Now, what if I'm finishing? I'm done with this. What should I do with the neighbors? Should I fill those or no? They said yes. You need to shift. So if you have bigger image, I will start from the top left corner, Y top left. we call this corner, place a name before. The origin. This is the 0, 0. This is my origin. Okay? Where the x equals 0, y equals 0. So that's why all my calculation will start from the top left. Okay? So if I apply the filter to the top left, to the top left side of the image, and will do this process, I will generate the middle value here. Then I will shift it 1 pixel. We calculate the neighbor pixel here. Shift it 1 pixel. Neighbor pixel here. Shift it 1 pixel. 1 pixel. Until I finish the entire row. Then I will shift down 1 pixel. So it will look, fill this pixel, then fill this, then fill this, then fill this, until fill this. Then I will shift down again, and I'll keep doing this until I finish the whole entire newer image. Okay, so this is what we call the cross correlation. So this U and V are the shift that we are doing, and this I and J, the corresponding value in the output image. So I will keep shifting. I will keep shifting U and V over all the rows. Then I will shift down 1 pixel, and we'll keep doing this again and again and again this way. Okay. What is the symbol for this cross correlation process? That's how it looks like. So when we are saying H, which is our filter, applied or cross correlated with F, which is my image, it will produce new image called G. Okay? Now, this makes sense because we are working with the cross correlation. Now, what's the difference between the cross correlation and the convolution? They said the convolution is exactly the same cross correlation process with one small tiny difference. Before applying the filter to the image, you have to flip it horizontally and vertically. That's it. This is the only difference between cross correlation and convolution. If I apply the filter as it is, it's a cross correlation. If I flipped it first horizontally and vertically, it becomes a convolution. So if you go to the example we are having here, I'm applying it as it is right now, right? Now, if this a correlation, cross correlation or convolution? Cross correlation, because I'm applying it as it is. If I want to apply or use it as a convolution, what should I do? Flip it twice, horizontally and vertically. So I will start by the horizontal flip. Horizontal flip mean anything up will go, sorry, anything down will go up, anything up will go down. So I will put my hand like this and put this up, put this down. So it will be 1.5, 0.50, 0, 0, 0.
So the middle always stays the same?
For that,
The middle is always gonna stay the same.
for now, yes. Okay, now I will flip it vertically. So in this case, I will put my hand like this and flip. So it will be 0.5, 1.5, 0, 0, 0, 0, 0, 0. Now, if I apply this to the image, it's a convolution. Is it clear? So cross correlation, I'm applying the filter with no flips. If I'm flipping it horizontally and vertically, it becomes cross correlation will convert it to convolution. Okay. Again. Now, can the correlation be equivalent to the convolution?
Yeah.
Symmetric around?
Or I think.
The bottom of it. Yeah.
Use.
Much time. Wow. Boy, skip flipping. Now, if I apply this one, flip it horizontal and vertically, anything will happen? No, I produce the same filter again. Okay, so if the filter is symmetric horizontally and vertically, in this case, convolution will become cross correlation, no difference. So the problem only occurs if the filter is not symmetric. If the filter is symmetric, you have to do this flipping process. Okay? Now, what is the symbol for the convolution? The symbol for convolution is this star, asterisk. So you are saying H convoluted F, we are giving them the asterisk sign. The convolution has the two properties of many mathematical operations, which are commutative and associative. What is the meaning of commutative and associative? If I have A convoluted B convoluted C, I can start with any two couples first. So I can start with, or I can start with B convoluted C, then convolute B, sorry, A, and so on. It doesn't matter. This is the associativity. What is the meaning of commutative? You can flip them, it doesn't matter. Okay? So the convolution is commutative and associative. It doesn't have a problem with this process. Okay? And it's linear. Okay? So the convolution, one of the drawbacks of the convolution process, it's linearity. And we will come to this problem later when we go to the neural network. That's why when they designed the convolution neural network, they introduced the concept of activation function. Because without activation function, the convolution will become nothing, will become linear. Okay? So let's see how it will work. So actually, let me activate the animation here, so you can see how this is working. Okay, so assume that I have image F, and I'm applying filter H. While I'm doing convolution, the first thing is flip horizontal, flip vertical, horizontal, vertical. Then apply it to the image. Where? Top left corner. Do the masking process, then shift until you finish scanning all the image. So going like this. That's how the pattern should look like until you finish it on the last position here. Okay? Let's see an example. Assume that I'm having this image. So this is an image. Okay? And I want to apply convolution to this image with this filter. The filter look like this. 1/9 and fills all with 1. Okay? Now, what is the first step I should do?
Horizontal, it's gonna work.
Now, not letting you do anything here. Why? Symmetry. Okay? So in this case, I don't need to do the flipping because flipping it will do nothing. The output of the flip exactly at the end. Okay? So I will start by applying the filter. If I apply the filter, that's what we'll get. Let's take it step by step. So I'll apply to the first value here. Again, we are applying it on the top left corner. Okay? So 1/9, all ones, apply to this part. Now calculate with me. 0 plus 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 0. Result is 0. Where should I put this 0? As I said, I'm having now a new image and an output. So this is my output. The value of this 0 will be added to the orientation or the point of the middle of my filter. Okay, so this position will be have our 0. How about the pixels up and the pixel to the left disappear? I don't have them. So the first value I will fill here in this filter, the one in the middle, up and left, completely disappear. Then I will shift one step to the right. Again, I will multiply each corresponding one to the corresponding place and add. So it will be 0 plus 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 9. 9 divided by 9 equal 10. Again, I'm adding to which position? This position. Then shift one more. Again, do the same game with me. Zero plus 0 plus 0 plus 0 plus 0 plus 0 plus 0 plus 90 plus 90. So it's 180. 180 divided over 9 equal 20. Again, which position? This. Keep shifting. I think it's obvious right now. So zeros plus 270. 270 divided by 9 equal 30. Again, which position? This one in the middle. Keep doing it. 30. 30. Then it will reduce back to 20 when it's here. 20. Then 10. Then I'm done with the image. Then I will go down one more position. 0. 20, 40, and so on. After finishing this row, I'll go next again, down, scan, next down, scan, and so on. So if I did this, I will find this is my final output. Now, is there a relation between the size of the image, the size of the filter, and the size of the output? Let's see. What's the size of this image?
Nine by nine.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 by 10. What is the size of my filter? What is the size of the output? Eight by 8. Count. 1, 2, 3, 4, 5, 6, 7, 8. Which makes sense because I lost one row and one column, right? One up, one down, one side, one side. So 10 by 10 converted to 8 by 8. Can this relate by any chance to the size of the filter? Actually, yes. So if the size of the input is 7 by 7 as an example, and the filter is 3 by 3, now count with me. 1, 2, 3, 4, 5. So the output will be 5 by 5. Which means this size reduced by what? 2. And the filter size is 3 by 3. Can we put the relation between them? The answer is yes. This is the relation. The relation is the output size equal the number, the size of the input image, minus the size of the filter plus 1. So here, 7 minus 3 plus 1 equal 5. If we go up to this one, 10 minus 3 plus 1 equal. So we can relate the size of the output to the size of the input and size of the filter. There is a relation between them. Is it clear? Okay. Can I overcome this? Like, is this a problem or not? Why?
Using pixels.
So the image is vanishing, right? If I have if the image is by default is small, it will lose some information. Can I overcome this? They said yes. How? They said by something called padding. What is the meaning of padding? I'm adding extra pixels by myself to surround the original one. So for example, in this case, the original one was 7 by 7. I'm adding extra row up and extra row down. Extra column left, extra column right. So the size after modification will be 9 by 9. Right? Now, let's apply the same equation that we discussed right now. So it will be 9 minus 3 plus 1 equal 7. So it's the same exact as the original one. Okay? So this way, I added extra pixel by myself to cover the surrounding just to guarantee that the output size will equal to the input size. Can we modify the equation to include this change? The answer is yes. And this is the modification. So original image size minus the filter size plus 1 plus 2b will be in the number of banded pixels. So here I will add 1 pixel to the side, 2 because I'm doubling it this way and this way. Okay. Now the question is, should I add to in those padded pixels? I'm adding something by my own. Those pixels exist before or no? No. This is something that I'm adding to the image. Okay? Then what I should add to in them? Actually, there are several schools for this problem, and it's problem dependent. Some people say add zeros. Just the zeros, don't add any extra information. Okay? When I add zeros, the zero represent which color in the grayscale level? The black. So this means I'm adding black pixels around. So this is one technique. Pad with zeros, with black pixels. Some people said no. Adding zeros means you are, when you are processing the filter here, this value of the output will be affected with those zeros, right? So I'm changing some information from the image. The value here in the corner is not zero, and the original neighbors are not zero. So when we modify it as a combination with zeros, I'm changing the nature of the image, which is not a good thing. Then if we were not adding zero, what should we add? They said, okay, we have another suggestion. Let's copy the last pixel up. So, as an example, you see this last picture was what? A pixel was zero. So I will add zero here. If the last pixel here was, if the last pixel here was 10, then the upper one will be 10. Whatever was in the last one, copy it up. I don't care whatever it is. I'm just extend it. And the last thing goes down, copy it down. The last thing to the right, to the left, put it to the left. Last thing to the right, put it to the right. This way, I'm adding some useful information to the image, rather than adding zeros. Some people said no. This is not a good technique. I will fill this bagging value with a mirror of the pixel. What does this mean? They said, I will consider this as a mirror line, and whenever here, I will copy it here. Sorry, mirror it here. Same thing here, same thing here, same thing here. So this is the mirror technique. Some people said no, not this nor this, neither nor. So what I will do, I will consider the image as a cylinder. So this last part is connected to the previous part. And this last part from here connected to the previous part from here. Last part from here connected to the previous part from here, and so vice versa. So I will copy from the right, add to the left. Copy from the left, add to the right. Copy from bottom, put up. Copy from up, put down. So I will wrap it, consider it as continuous surface. Okay. And all of those considered to be a correct padding technique. Which one of them is the commonly used? This is the most commonly used one. It's simple. Just add a couple of zeros. That's it. So you don't have to take care of blend or mirroring or wrapping. It doesn't matter. Okay?
What happens if there's more than 255
What do you mean?
pixels? Pixels been reduced. Like what if it's bigger than, what is it, like 12 by 12?
You mean the filter size? I say, what do you mean?
The whole image.
It's talking about the input size.
Yeah, the input size. Doesn't the input size have to not go higher than 255?
Okay. Now you are confusing yourself between the image dimension and the pixel value.
Oh, okay.
Pixel value should not go over 255.
Yeah.
Image dimension can go any value.
Uh,
So there is no restriction on those numbers. Can be any number. But the pixel value should be 255 maximum. Okay? Is this clear? Now, actually, this is one of the good questions that we have. Or are the filters should be always 3 by 3? Can it be bigger? Can it be smaller?
Yes.
Okay, you said yes. So what are the smaller filter value that you can use?
2 by 2, right? 1 by.
Can we use smaller than that? Actually, yes. In some cases, you will see that we are using filter 1 by 1. For some reasons later, when we study the neural network, you will see that we are using them for one reason. We will study it. But mostly, in most cases, the filter will be odd size, not even. Why? The problem of the middle point. Okay? Now, the middle point is clearly stated here. If it's even, then which point I should choose? If it's 2 by 2, then where should I put the output? At which point? Here, or there, or where? So it's a confusing a little bit. Does this mean that there is no even filter? No, there are. As you will see later in the differential. If we use filter for differentiation or to find the derivative, we are using sometimes even filters. But it's rarely used, and even this type of filter for the differentiation, we get rid of it. They are not using it nowadays. They always use odd size filters. Okay? That's why if you are using the OpenCV and you try by any chance to put the filter size 4 or 8 or something, to give you an error. To not work. Because the default filter size right now is odd, not even. Okay? Now, there's one more trick. What is this trick? Always bad with 1 pixel? Or can we bad with more than? Like, can I add 2 pixels here? Three pixels, 4 pixels?
Yes.
This is a good thing or a bad thing?
It's a bad thing because we are just increasing the border size.
Thing because we add zeros. Basically, we add nothing, no information. Okay? So the number of padding bits mainly determined with this relation. The number of bad bits equal the filter size minus 1 over 2. Okay? So if I have 3 by 3, in this case, 3 minus 1 equal 2. 2 over 2 equal 1. So I will pad with 1 pixel. If the filter size is 5 by 5, there are filters with 5 by 5, and we use it also. 5 by 5, 5 minus 1 equal 4 over 2 equal 2. Then I will pad 2 pixels. If I want to preserve the output size, meaning I want the output size equal the input size. Okay? Another trick. In all the examples that I show you right now, for all the convolution process, I'm moving the filter 1 pixel, 1 position, right? Look, shift 1 pixel, 1 pixel, 1 pixel, 1 pixel. Does this mean that I have to shift 1 pixel always? Can I shift more? The answer is yes, I can. And in this case, I can move even more. So I start from here. See, this is the original position. Next position will be here. This way I move 2 pixels. Next one will be here. In this case, the output will be what? 3 by 3. So the 7 by 7 with a filter 3 by 3, but the output will become 3 by 3. Why? Because I moved or shifted 2 pixels. We are calling the number of pixels that we use for shift stride. So here the stride equal to 2 pixels. Okay? Originally the stride was 1. Now the stride equal 2. Can I have a stride here equal 3? Originally I'm started from here. If I use a stride equal 3, this means that I will shift 3 pixels like this. So can I make another shift?
No.
I will go out of the image this way, right? So this last column has been lost. I can't use it. So the output will be 2 by 2. 1, 2. And I lost this one. So the output is okay. So choosing the stride number is tricky. That's why in most cases we stay on the safe side by having the stride equal 1. The stride equal 1 will work with all image, no problem. Okay. If you increase the stride number, you have to watch out to avoid losing some information. So stride equal 2 or 3 or higher agree or happen in some cases, again, as we'll see later. But it may cause image loss or data loss. Is this clear? I leave it to you right now to think if I can modify this equation by adding the stride information. Think of it until next lecture, okay? Because we can add this information here. Think of it until we come to the next lecture, okay? Now, based on what we learned so far, assume that I'm having this image and I apply this filter to it with padding. See any change to the image? So I'm adding this here to the top right corner. It's 1, all zeros. I will add those together so the pixel on the middle will be converted here. So did I do anything? No. That's why this is called identity filter. I'm doing nothing. I'm copying the pixel in the middle to the position here. Okay? If you are not using padding, what will be the effect? Without padding, what will be the effect of this filter? Reduce the size. That's it. So you are getting rid of the first row and first column on the side. That's it. Okay? Now, what if I move this one here to the left? You will find that the output will shift it. So it will leave the last row, the last column blank. Okay? Now, what if I do this? Remember this filter that you used in the beginning, right? In the example. What exactly, or how this will affect the image? What happened here? The image become more blurry. Okay, so it become unclear and blurry. This type of filter has many names. It named mean filter, Really annoying. Mean filter. Why? Because it finds the mean of all the image within this range. As if we are adding them, divide over 9. Add all of them, divide over 9. So it's mean. Okay? So this is one of the mean of the names for this filter. Another name is blurring filter because it removes the edges. You see here, I can easily state that this is the eye area, right? Sharp, the image is sharp. You see here, the image, the eye area become one piece with the white area. So the white area now is not separable as here, okay? So this filter will make it more difficult and blur the image. Now, can I use this to sharpen the image? The answer is yes. How? Actually, you can do small trick. From this, assume that I have my image I, and I convolute it with this H mean. What's wrong? You know what? Seriously? The computer is playing games with me. Okay. Okay. So this image I convoluted with H mean. The output is I mean. Agree? Now, what if I subtracted this from the original image? This is an averaged image, right? I will subtract it from the original image. What will be the output? Imagine that. You subtract this from this. Edges. Image that only include the edges, right? Because here I destroy the edges. So I'm subtracting this from the original image, which has edges. The output here will be the edges, right? Now, what if I added this back to the original image?
Then I get sharp.
Exactly. So this will make eye sharper. Now you do the math. Substitute with the eye mean here by this. Substitute with the eye edge here by this. You will find that what we did in this was double the identity minus the mean filter. So the result will be a sharpened version of the image. Okay? So 2 identity filter, HI, minus H mean. And result in H sharp. So I can play with the filters to produce another type of filter that do different function. Is it clear? Okay. So this is an example after applying this over the whole entire image. You see, the output here is what? More sharp. Okay. And we can do this actually for any blurred image that you have from your phone or from your camera. You can play this trick over them to make them more clear and sharp. Okay. And you will do another technique later, maybe next week, if we want to increase the size. So if you have image 10 by 10 and you want to make it 20 by 20 and we be sharp as well, we will learn how we can do this. Okay. So as I said, this is what we call the mean filter. Okay. What exactly the property of the filter to call it mean? The filter to be called a mean filter, it has to satisfy two conditions. What are those two conditions? Did anyone recognize them?
Yes, the arrow to the same. Middle value.
What that?
Middle value.
Middle value? What's wrong with the middle value? This condition, the size must be odd. There is no mean filter with even size. Impossible. Second, sum of all values equal 1. And all of those, the result will be 1. Okay? So if the filter satisfies those two conditions, it can be considered as a mean filter. And in most cases, it's symmetry around X and Y. Okay? Now, this one considered to be a mean filter, and we tested and we find that it's a mean filter, right? If it's the only mean filter we can use, we said no. This is called the cubic mean, because all the values here are similar, right? Can the values here be different and still satisfy those two conditions? The answer is yes. Like what? Like this filter. What is this filter? This is called a Gaussian filter. And remember this name and memorize it, because we will use it a lot. Gaussian filter is one of the main filters that we will use all over the semester. Until we finish the semester with the neural network and the stuff, we will use the Gaussian filter. Okay? So the Gaussian filter is a filter that follows bell-shape, the Gaussian distribution, which has bigger value from the middle, lower value from the direct edges, more lower on the corners. But still satisfy the condition that the sum of elements equal 1. That's why we divide over 16. If you add those, the result will be 16. That's why we divide over 1 over 16. Okay? Now, is it symmetry? Yes. Okay? Does all the value equal? No. Okay? So, this one will give more focusing on the middle points rather than the edges. The other one, this one, give all of them the same weight. That's why it's called mean. I'm averaging them. This one give more power to the middle one over the other edge. Can we compare the result of both of them? The answer is yes. If this is the image and I want to apply the traditional mean filter and the Gaussian filter, that will be the result between them. Can you see the difference? What's the difference?
CL is more blurred.
But also, it didn't destroy the information as the mean filter. As an example, you see this side, you still can see it. You see this one, you still can see it. You see this one, you still can see it. Look here, they merge the little bits. So the Gaussian filter can blur efficiently and still preserve some information. Here, it's more messy. Okay? That's why in most cases, when we start to do the mean filter or the mean or pruning process, we will use the Gaussian one rather than the mean one. And there is a mathematical proof that we'll go through next time. Okay? Any questions? Okay. So next time we'll see how can we implement this convolution process again with the program, with programming. Because next time we will have next assignment. Then we'll learn more about the filtration and how we can use this filtration process for more than one application and the super resolution technique. Okay? Any questions?
So the assignment tonight is gonna be due by next week, right?
And the zip file was locked.
The file what?
The file was locked. Zip file was
Still locked?
Yep.
Still?
Yep. The zip file. Have a look.
All of you see it locked?
No, I have it unlocked.
The zip also?
No, I don't have it locked.
So you can download them?
Yep.
Both?
What?
Then use another browser. Maybe the other browser can have a problem. If you see any of those problems at any time, please let me know.